Justin and I actually overlapped in doing our PhDs together up on the fourth floor. I know a lot of you don't know what goes on the fourth floor, so it's actually great to bring Justin down here. I invited Justin to come chat with us because while a lot of people here in the Fisheries Center, or IOF, I should say, Institute for Oceans and Fisheries, work with a lot of the outputs from IPCC scenarios and climate change models, Justin does a lot of research on more of the inputs, and basically in the great kind of integrated modeling that goes on with IPCC scenarios, there's the energetic economics aspects of it, and then the climate models, and then the output which we use for fisheries and things like that. And just given the kind of interdisciplinary nature of our department, I thought it would be really great to have Justin come down and really give us kind of nuts and bolts about what goes in, and also some of the problems with some of the more prominent IPCC models. Justin has a background in engineering. He has recently finished his PhD. This work is largely going to be on his PhD work, and he's currently doing a postdoc again on the fourth floor. So he'll be around, so you guys can come chat with him and everything. And I'll hand it off to Justin.
Yeah, thank you, Gerald. I appreciate that you took the time on the long weekend right around the corner and beautiful afternoon to come and talk about this. And so what I'm going to be talking about today are integrated assessment models, which are underlying the plausible basis for a lot of the climate scenarios that have been used in downstream research like Earth systems models or GCMs, and probably some of you work with ESMs or GCMs. And so analyzing a lot of the scenarios, they'll be the RCP scenarios like I'm talking about today that are articulated and detailed by the integrated assessment models. So what I'll talk about is the scenario design process for CMIP5 and CMIP6 that chose the RCP 8.5 scenario as the upper bound, and for CMIP6 this is the SSP5 RCP 8.5 scenario. And then because the scenarios are so focused on coal and high levels of coal use in terms of industrial fossil fuel emissions, I'll talk about why those energy system outlooks became so prominent in terms of the integrated assessment models that produced them, and talk about whether they're plausible today. And then maybe in the discussion period after, in questions, I've got some extra slides that when I was reviewing this and thinking, oh man, that's just a lot of material. And so there's another chapter in my PhD thesis that looks at if there's not as much coal, or coal is not such a dominant technology in the future, or there's still ways to get to RCP 8.5 using tar sands or changes in ocean or land sinks, and so we can look at those kinds of issues. And so to get into it in part one, we'll just talk about the scenario design process. So a lot of climate scenarios used in the Earth systems, climate change research community, fossil fuel emission component, they're based on these models of long-run economic development and energy use. And these are a class of models that have been developed and applied since the 1980s. And so Jay Edmonds and John Riley in 1983, they really put together some of the prototypical long-run energy development models that many of the integrated assessment models are built on today. And so the IPCC assessment process that helped organize and bring all these disparate energy economy modelers together, and then used and applied their work to create these common sets of emission and climate scenarios. And so the examples are in the first and second IPCC assessments, the IS92 scenarios, and then special report on emission scenarios, which we're using for the RCPs, and then now the RCPs and SSPs. And basically what an integrated assessment model is it's a single model that has a very simple representation of economic growth, economic development, of the climate. So like the magic climate model is commonly used in a lot of integrated assessment models, of land use and of the energy system, energy technology and productivity, and how energy technologies could develop in the future. And so it helps us answer questions of, if we take a GDP growth scenario for a particular country or for the world, and then we assume different developments in energy technology and how that plays out with urban land development or rural land development, how many degrees Celsius or what kind of policies could interact with any of those components to reduce and mitigate effects of climate change. And so the basic approach of integrated assessment models is that they use this equation, this chi identity, in order to express a scenario of CO2 emissions in the future. So it's really fossil fuel emissions are based on a population scenario, an affluent scenario, so GDP per population, the energy intensity of that GDP, so energy per unit of GDP, and the carbon intensity of that energy, so which technology and combinations of technologies are we using? Are we using more coal-intensive, more carbon-intensive technologies, or less carbon-intensive technologies like hydro or nuclear renewables? So going back to the scenarios that have been used in the IPCC assessment process for a long time, the Special Report on Emission Scenarios released in the year 2000 had created this prototype for how all the scenarios are coordinated amongst all the different groups that do research on climate change. And so these scenarios are all based on 21st century developments in global society that, I don't know if I'm blocking everyone on this side, but whether you can see kind of 4 different boxes that a lot of different integrated assessment models would then map out how these would look. So from developments that were more focused on economic development or rapid GDP growth, to more environmentally aware societies, to more regional access, more regional development versus more integrated, globalized global development. So based on all of those different narratives and all the different integrated assessment models, it produced this range of scenarios that look something like this for the 21st century, from 2000 to 2100, and I think I have a laser point on this thing, yeah. So you can see this range of annual greenhouse gas emissions all the way up to the maximum range, which overshot this top axis here, and then all the way down to the minimum. And all of these are expressing the B1 and B2 and all of these, which are the codes for how they map to those different types of development. And these all created the uncertainty span for future fossil fuel emissions and total radiative forcing that were then used by more complex climate models. And so after the 3rd and 4th IPCC assessments, there was this focus on building a successor to the Special Report on Emission Scenarios. And so what the community that develops the scenarios, what they decided to do was to take these 4 endpoints for possible year 2100 radiative forcing, drawn from all those published scenarios that I was showing you in that range, and then select 4 representative scenarios from all of those. So the RCP8.5 scenario was the high, the RCP6 and 4.5 were intermediate, and the RCP2.6 was the low. And it was intended to represent mitigation steps because we're already above 2.6 watts per meter squared of radiative forcing now. So to get down to that level, we'd have to take some concerted action to reach it. And although these were simply GHG concentration scenarios, we often think of them in the same way as those SRS scenarios. And the SSP scenarios are actually now building on that and making them more like the SRS scenarios, which we'll talk about. So this is what all the different RCP scenarios look like, from the high to the low levels. And so they're really just based on taking those old scenarios and then drawing the endpoints out and producing pathways that connect it from the past to 2100. But an interesting thing when you look at all those SRS scenarios that were really up above this level, they were all based on outlooks for vast coal expansion. We'll talk about why for a minute. And the other thing to take away is that all of these RCP scenarios, when you're using them in your work, they're representing a wide array of these integrated assessment model energy supply and demand scenarios. So different combinations of technology can produce the same RCP. So now in CMIP 6 and preparing for that IPCC 6 assessment, there's adding another layer of complexity to all this, as if it wasn't confusing enough with all these numbers and acronyms already. And so in the past, we had, say, in CMIP 5, the RCP 4.5 scenario, which was just one-dimensional. Now there's all of these different narratives. There's 5 different narratives of global development that can map to each of those forcing levels. Okay? So the 8.5, the 6, the 4.5, and the 2.6 can all be reached in different ways based on these SSP scenarios. And the SSP scenarios are just building on all of those narratives of the previous set of scenarios. And so then for CNIP 6, you get this of all these different combinations. So you'll see this increasingly in GCM and ESM outputs and so on. So here's what that whole range looks like, which is basically the same as what was used for the IPCC's 5th assessment, but you just add these SSP scenarios in. So what they are giving you is they're giving you the precise kinds of technological developments in terms of energy technology that can lead to these levels of radiative forcing at the end of the century. So even today, the RCP8.5 and SSP5 scenario is being used as this upper bound, so is it still plausible? So this is one of the chapters of my PhD thesis that I wanted to look into. And in order to frame it, I think me coming from an engineering background, coming from an energy background and techno-economic analysis, this is really how I think in terms of global primary energy supply and the kinds of technologies that are used to supply economic development around the world. And so primary energy is a measure of the energy contained in resources before they're transformed or converted or transported for end use to power our lights or fly planes and drive cars and so on. So this is what it looked like post-World War II, growing primary energy supply with increasing oil and natural gas and coal and nuclear and hydro renewables. And so if we expand that axis out to 2100 and we just look at what the composition of world energy supply is right now, it's 550 exajoules. That's the number we use to quantify that. And then the composition is about 1/3 oil, about 1/4 natural gas and coal, about 5% nuclear, and about 10% hydro renewables. So what would it take to get to an RCP8.5 kind of emission scenario like is used in the original RCP8.5 scenario from 2011 or the SSP5 8.5 scenario? Well, here's what it would take in order to transform into that kind of energy system. We'd have to use 3 times more total energy, and then most of that energy would come from coal, actually. More than half would come from coal. And then natural gas and oil would face significant declines. Nuclear would grow, but renewables and hydro remain about the same. So if we compare that in 2100 to RCP8.5 kind of energy supply, and this is from the Ryaki 2011 paper that described the RCP8.5 scenario, we need to transition something like this from much less coal use as percentage of overall energy supply and much more coal use in absolute numbers as well by 2100. And most of that transition would start around mid-century as gas and oil really reach their peak output. So why is that? Why would that happen in the future? So since the 1970s, these coal-dominated worlds have been a part of climate science and policy. And it's this hypothesis that the global energy system would transition to one dominated by coal around the century. And since coal hasn't been the dominant energy source since the 1950s, where does this assumption really come from? So it started in the 1970s energy crisis. It had been around before then, but with all the anxiety that was happening at the time around gas lines and high oil prices and coming up against decades of really unabated expansion of gasoline infrastructure, cars, and roads in Western Europe and North America, it was a real shock to the system. And policymakers and engineering community, they were looking at ways that if, for example, in the US, if there could be oil supplies that could be secured, what could we do in order to make sure that we could continue that kind of high automobile-intensive lifestyle? And so the answer was coal, because the United States is very much the Saudi Arabia of coal. It has large domestic coal supplies, as well as in the contiguous states, but also in Alaska, some of the world's largest amounts of coal resources. And so the idea was there is a virtually limitless supply of coal, if not in the United States, in China, in Europe, in the Arctic, and this coal could be extracted at a lower cost than any other alternative, and all else equal, coal was this backstop energy supply if everything else failed. And that all of these coal recovery technologies, even though it's a bit ambitious to project it, they could potentially achieve these unforeseen and unanticipated drastic specific technology improvement rates that were several times historically observed average. And so this was all articulated and developed and made a part of these energy models that became integrated assessment models alongside these oil crises. And a lot of the people who were tackling these energy challenges, who were part of those energy studies at that time, went on to form the basis of the integrated assessment modeling community. So if we look at these late 1970s perspectives on oil, there was a workshop at MIT, it was called the Workshop on Alternative Energy Strategies, and one excerpt from the report stated that oil exhaustion curves generated by this project showed global output peaking as early as 1990 and no later than the year 2004, with the most likely timing of peak production between 1994 and 1997, which nowhere close to that in a US CIA report, which was particularly dire. The argument was that the global oil output must fall within the decade ahead, and as a result, the world can no longer count on increasing oil production to meet its energy needs, and it does not have years in which to make a smooth transition to alternative energy sources. So, given everything that was happening in global north at the time, in those societies, the level of fear around energy supplies, the anxiety was quite palpable, and so these studies reflected that. And so, one of the studies that was produced in that context was part of the International Institute for Applied Systems Analysis in Austria. They were part of this joint funding between East and West to look at the global energy challenges, look at global energy development, and how could we think about meeting the world's energy needs well into the future. And so they created the message energy model in 1981, published a study that looked at what could potentially happen in terms of the global energy mix. And so conventional oil, like the oil we've been using for a long time, it was considered that it didn't have much room to grow. With that unconventional oil, like say tar sands or fracking, oil shale, it could be the source that really grew. But even eventually that would reach limits, and then we would have to turn to cold liquids, like this coal backstop technology. And cold liquids technology has been used for a long time in South Africa. It was used in Nazi Germany. It's a lot of regimes that are very isolated have turned to cold liquids. But in recent years, China has funded a lot of cold liquids development projects because they have so much coal. And when you can site cold liquids facilities near a large coal mine and the economics make sense, then they can be used to produce oil out of coal. So they would produce these projections of global primary energy of these high and low scenarios. And one of the advantages of being in the future is now we can look back in retrospective and see how it actually performed over time. And so this green line is showing the historical development path versus the high and low scenario that was developed back then. And we actually undershot even the low scenario in terms of the total overall amount of primary energy that was used in the world. Now, so how did we do in terms of the range of coal projections that this model made? Well, we ended up even under the low scenario, and that's with the massive expansion of coal around the world that's happened in the early 21st century in China and in India, and just to catch up to the lower bound of what that was looking like from these projections that were made back in the 1970s. Now, how do we do in terms of oil? Well, we actually ended up above the low scenario for oil, and I'm going to talk about why that is. It was underestimated oil supply demand from these kinds of integrated energy models. So what are the total primary energy supply scenarios from the message model look like 40 years later? Well, they're this, which is the message energy model, which is in the Ryabi 2011 paper on RCP8.5 of high levels of coal use and declining oil. And that's because the basic structure of how this model solves for energy supply and demand is essentially exactly the same as how it was back in the 1970s and 80s. So why is it that RCP8.5 and other business as usual scenarios like this anticipate future coal dominance? Well, first off, RCP8.5 scenario as an upper bound is a high scenario. It's designed to show the use of all the theoretically extractable fossil occurrences from the literature. So that's the first part. So it's looking at what's that ultimate potential of fossil resources and what if we combusted them all by 2100. So that's the first part of it. So it is this hypothetical kind of thought experiment of just saying, what if this were to happen? But here's the main reason why I argue in my work that this view, this perspective, is really outdated. It's because we have to have a way of looking at the total amount of geological energy resources that exist and dividing it up into those that are economically accessible, right? And so energy economists do this all the time. We have a total amount of oil resources in the world, and then we have to figure out how many we can get to in a reasonable amount of time. So we have these two dimensions of economics, so the feasibility of economic recovery, which relies on markets and demand and technology and technological potentials, and then also the geology of the degree of geologic certainty. Does it exist? Can we get to it? And so that gives us this category of reserves, and reserves are this portion of the oil resource or gas resource or coal resource that we can reasonably get to with today's technology and potential. And so then there are, based on varying degrees of geologic certainty and economic feasibility, we get this large box of unconventional and low-grade occurrences of any resource, and then the reserves and the total resources. And then within each of these categories, we can divide it up even more and look at recoverable versus sub-economic versus non-economic and label it that way. And then within reserves, we have categories of proved or probable or possible. And then some of these resources are undiscovered based on the geologic features of a region. We would expect to find those types of resources there, but we haven't actually gone out to map them in detail. So they're hypothetical and labeled prognostic or speculative. And so what integrated assessment models have to do, because they're looking out across 80 years or more and producing these scenarios, is they have to anticipate some way of how these resources become reserves or reserves become resources. And how we think about this process makes a really big difference in determining the ultimate potential. And so one way of looking at that question is the reserves to production ratio. So these reserves, the definition is that they're the fraction of the geological resources that are economically recoverable, like I was showing in this box before. And the energy economy models that are used, like MESSAGE and with other integrated assessment models, they're built on the assumption that all known geological occurrences of energy resources can eventually become reserves, maintaining something called an equilibrium reserves to production ratio. So I'm going to explain what that means in just a minute. But just to illustrate how this stacks up in the case of oil, so in the year 2016, there were 7,000 exajoules of oil reserves around the world of conventional oil. So we were producing about 180, and so we divide the oil reserves by production that year, and we get about 40. So based on today's technology, today's economics and prices and demand, about 40 years of production would exhaust those reserves. But if we look at the total amount of resources of that full box, we get something like 80 years. And then we're always finding new resources or current resources. It turns out that we can't get to them or they're not accessible. So that number is constantly in flux. It's constantly changing. So in preparation for the IPCC fifth assessment, all the integrated assessment modeling teams, they got together and started producing scenarios and looked at all of the different fossil resources, oil, gas, coal, and looked at that ultimate potential. Well, I think one thing that really stands out here in terms of the total resource number is just how much coal there is in total resources in the Earth's crust. So if we look at all of the Earth's crust, it's a tremendous amount of coal that is there. We're talking about millennia worth of coal compared to today's production rates versus oil or gas. So in terms of total coal resources, we're talking about 38 times more ultimate coal than oil, 24 times more ultimate coal than gas, and that's where this idea of the coal backstop comes from. It's that if we run out of oil and gas, we can use coal to replace the ways we use them, and in that sense, when we look at that ultimate number, even an 8-fold expansion in coal production looks conservative. But the real question is today's technology or future technologies actually able to recover anywhere close to that amount of coal? And so we can go back to this idea of equilibrium reserves to production ratio. And I'm just going to check on how I'm doing on time. So I'm coming just in the last few slides here, and then we can get to questions. So what this is reflecting, what energy economists do with this reserves to production ratio is they're trying to anticipate how changes in production change incentives to explore for more. And so that's what's happened in oil. Since the 1960s, we had a reserves to production ratio in oil of about 25, and now we're up around 50 today. And that's because as there's been more production, it has created an incentive to explore for more. In coal, however, back in 1965, we had numbers that were 800, 900, 1,000 for the reserves to production ratio, and I'll highlight that that's an axis break here. And that number has continually declined. As coal production has increased, we're not finding significantly larger amounts of reserves. And so this is reflecting the technical progress trend for oil, and this is reflecting the technical progress trend for coal. And so it's important to include that in how we're thinking about integrated assessment model scenarios. So a large reason why we know a lot more about coal now than we did 15 or 20 years ago is mainly because there was a significant concern in the climate community. What happens if China really turns the taps on its coal resources and goes all in on coal-fired development? And that happened in many ways. And so what we see for annual coal production from the 1990s until just recently, it essentially doubled over that time period. And it reached a peak around 2013, and it's come down just a little bit, but it's hovering right around that level. Prices went up. That's the key thing to note, is that prices for coal, even with not as much coal expansion that's happening now, prices are really staying at quite a high level, which means it's not quite as competitive. But one of the things that I did in my thesis chapter is try to explain the difference between these legacy assessments of coal that anticipated all this coal and modern assessments of coal. And so really the factors are that higher prices in production have created economic incentive to improve information, but that's meant that we found that all the coal that was out there actually wasn't as accessible as we thought it was, and I can talk about reasons for that in the Q&A. There's systematic overestimates of the way that coal was assessed in different regions that actually fed into this large overestimate of coal that then, when there was the incentive to go back and improve the information, it turned out a lot less was actually recoverable. Also improvements in assessment technology like GIS and satellites and better database systems have improved overcounting and made sure that double counting wasn't as prominent. Production technology actually has a big part to do with it, because high productivity longwall coal mining technology that is able to supply coal at that high production level, it can't access these small seams, and so the kinds of coal that can be categorized as reserves is actually declining. And so then international coordination and standards is another big factor of different countries, especially post USSR era, of looking at economic factors in terms of coal assessments, and what was accessible has made a big change. So I've got some different case studies on coal in the regions, International Energy Agency, other studies, recent developments in coal, like in India, where they canceled many coal plants, about 50 times as much coal as we use in Canada. They have canceled that many plants in just last decade, which is quite shocking. China's curtailing investment in coal, and World Net Additions and Carbon Brief actually have a really good article on this, which I recommend, about how we're looking at in the next decade reaching peak coal. And projections from just a few years ago of growing coal demand have been cut back significantly. So when we come back to the RCP8.5 scenario, we look at what it would take to reach the SSP RCP8.5 in terms of coal use per capita in the world. Here's the screen historical trend, and here's what it would take to do the RCP8.5 scenario. And so this is the full range of all the fifth assessment scenarios of what they look at for coal per capita. And so that's why I argue that a lot of the factors that are anticipated in these technical economic outlooks are really outdated. And so we have to look at other ways to potentially reach RCP8.5 to reduce use. And so in summary, RCPs and SSPs are selected from these ranges of energy technology outlooks produced by IAMs. The upper bound scenario of RCP8.5 has been based on coal-intensive scenarios of the past that hypothesize this maximum extent for coal combustion that's since been nullified. And China's massive expansion of coal in the early 21st century illustrated some elements of this development pathway, but also highlighted its limitations. And so it doesn't seem like a century of continued coal expansion is plausible, especially since India's canceled so many coal plants. All right, and that's it. I realized I shouldn't give a talk without a clock within my eyesight because my back to it was good the whole time. That was challenging.
So, I think thanks for giving the talk. Yeah, it's really useful because our team here often use a lot of the outputs of the different kind of models that then look at the outcomes of these different scenarios. So it's good to us to understand what key assumptions behind those integrated assessment models that drive, that provide the background for using those scenarios. I think that I'm interested to know is, so in this case, so it is physically possible to drive RCP8.5 through code environment. So it is more of a question of whether it is economically feasible or possible to that this scenario will emerge in the next few decades, given what has been happening with energy transition, the way the economy is going. So I think so that brings the questions about whether philosophically whether we still need to consider these less possible, but then still possible scenarios to give us a more extreme range of what may happen in the society, so that we can at least compare what the extreme are. Or we focus on the more narrow set of scenarios which are more bounded by what's happening now and what we believe in now that is more possible to happen. So what's your opinion on this?
Right. So I think that these kinds of extreme cold scenarios, their plausible basis doesn't really stand up anymore. And so looking at that higher end of an RCP8.5, we really need to try and illustrate in ways that don't involve this massive coal expansion. There still could be a lot of coal use, but maybe it's combinations of tar sands and coal or something along those lines. I actually think that even when you take all energy resources together, you're still looking at numbers that fall short of what it would take in terms of emissions to reach RCP8.5. And maybe the group in this room would know better than I would in terms of, say, ocean sinks and carbon sinks. Like, those are the factors that, even on a lower emission scenario pathway, if we really go with that SSP5 fossil fuel development, no holds barred, just we don't really care about anything related to the climate, and we just use as much fossil fuel as absolutely possible over the next 80 years. Even if that's not enough to reach those kinds of emission scenarios, what would happen in ocean sinks that maybe they're not as large as we expect? And so higher CO2 concentrations result in the atmosphere. I think that's really how I would see an RCP8.5 scenario actually happening. And my only real knowledge of ocean sinks is just reading a few papers and reading the carbon budget reports and seeing all the different modeling, but I'm not as familiar with it as I'm sure all of you are, and so it really, I'm just not sure what the ultimate worst case in terms of ocean sinks could be, or land use change too.
Thanks for that talk, it was really interesting, and as William was saying, I think it's really neat to get a better understanding of some of the assumptions. For me, like personally, I always think that assumptions are critical, and so I like to state them for my own work, and I really like to understand what they are for other people's work, and they tend to be hidden, and so it's really neat. Like it's not something that I've necessarily really heard about before or been aware of, so it's really neat to have that presented. So I actually have several questions. I'll try to keep them to the most essential. So the first one, based on what you presented, is simply like, why hasn't it been changed then? Like, why, given what you presented and the fact that that's been sort of like, maybe, people have been aware of it or maybe not, like why has there been no effort to sort of change some of the projections based on the fact that, well, it's been for a while now that coal hasn't been exploited to the point that it was projected originally. So why have there been no attempts made at revising it? That would be one. Then the second one would be, what would be based on your experience, and kind of like leading on from what William was saying, would it be better to use RCP 4.5 as a more realistic, potentially upper bound? And then whether maybe, I guess that without going too political, given that Trump is like now saying that coal is the new best thing, have you, like based on discussions that you have with your peers, are you seeing that there might be some changes in trends for other countries, since it's also economically and politically a sort of global bargaining power? Have you seen changes in direction of potentially re-engaging with coal exploitation?
Yeah, so great question. So first off, the first one is, why did the SSP5 RCP8.5 scenario end up looking exactly like the 2011 RCP8.5 and all the previous mega coal scenarios used all the way back until the late 70s? So I think the biggest factor there is one, academic inertia, and the speed at which the IPCC assessment process moves. So basically, it's very time consuming to be involved in these things if you're part of the author team. And so then by the time you're finished and complete one assessment and then move into papers that are published that are new in the area, and then you have to be part of the scenario design team that's making the new CM6 scenarios, for example, there's a very short window in which you can really get papers out to affect that process. And so I think that when we're talking about maybe the IPCC 7th assessment, it'll be different, right? But it didn't happen in time for the 6th assessment. So that's one of the factors. However, it is better in the sense that in the SSP scenarios, the SSP1 scenario was the first of all of the IPCC scenarios that actually had a peak in coal production this century. And so when you talk to geologists who work in this area, you know, it's very hard to specifically pin down when that peak might be. But you know it's coming eventually. Reserve assessments and the data that's in the different regions, and now even the International Energy Agency, one of the slides I skipped over just so we get questions, had to do with when that peak may be coming. And so if you looked at their reports 10 or 15 years ago, they would have said, well, you know, we don't foresee it in the near future. And now they're really saying that if India doesn't build all these coal plants, we're going to see a peak in coal production in the next decade, which is great in terms of CO2 emissions and climate, but we're still, you know, that peak needs to happen sooner and decline faster is really goal. So that's where policy intervention can play a role. So then your next question after why it hasn't changed was, what was it?
Good question, let me double check.
Which
one should we use? Yeah.
All right, so the RCP 4.5 scenario, in my opinion, is too low in order to capture total fossil potential. So going back to that SSP5 fossil fuel development type scenario where we don't care about greenhouse gas emissions, where we all just follow Trump, you know, off the cliff ledge or something like that, we would have enough fossil fuels that we would burn to go well above 4.5. And so let me see if I can actually go to one of the slides that clarifies that. So this is one that I made for the Pacific Energy Innovation Association when I talked to them about this, where this German Natural Resource Ministry, BGR, they do a very good job of looking at potentials of energy resources around the world, so reserves and resources and availability. And so all these data are based on that report. So if we go back to that McKelvey diagram of the different boxes of resources and reserves, and we just take conventional oil reserves in terms of unabated combustion of all the CO2 that's contained in them, and then the amount of CO2 in gigatons. This is where we sit with conventional oil. If we added all natural gas to that, we go there, and then all oil and gas resources plus reserves would be here. We can add coal, unconventional oil and gas, and then here's perfect recovery and combustion of all of those versus the RCP 4.5, the 6, and the 8.5. So that's why I'm saying that even if we combust all the coal that's this upper extent based on today's understanding now, there's still this gap between RCP 8.5, but if there are different factors in land use or ocean sinks, you could still do this or even less and potentially get RCP 8.5 levels of CO2 concentration. So that's why I would say 4.5 is too low. And somewhere between really the RCP 6 and 7 scenarios are more like the upper bound. So now for CNODE 6, they have the SSP2 scenario, that's SSP2 7 watts per meter squared. That's more like what I would consider the upper bound, plausible upper bound. And then you have one more.
Sorry, that was, and the last one is just.
Next time you do 2 questions, no more. No.
Yeah. So then it was it's Trump's rhetoric and pulling out of international agreements, changing what's happening in coal-fired development. So one, I think I've been very shocked in this field at how fast the U.S. is retiring coal plants. And it's going far faster than I ever thought.
Oh, so, really? So yeah. Trump says no, and then people are saying then it means let's go fast.
It's shocking how little effect he really has on this kind. And so I think some of the regulatory changes that his administration is pushing forward, it's absolutely slowing down the types of retirements that we will see in the next 10 years, but it's not reversing it. And that's because these trends that have been playing against coal, especially if we're just talking domestically in the United States, they've been happening for a very long time in terms of employment. And, from a political science standpoint, he's just really lying to people in coal communities to get their votes and say, hey, I'll bring it back to you. And he really can't. So that's one factor. In terms of the global perspective, with, say, China or India, looking at RCP8.5 potential, it's really what is Southeast Asia going to do? What is China going to do? What is India going to do? And that's where you get into the economic factors of, is coal this cheap, competitive energy resource? And it's really not. It's really proving not to be. And China continues curtailing its coal output of these small mines and limiting the amount of time that workers can be at coal plants because they're just producing too much coal. And then that's not even getting into the environmental factors of trying to maintain stability in China given political stability, given environmental concerns and so on. So that would be my comment there.
Thank you.
Yeah, so.
That's so surprising. Should I? No, so this picture is very good. So you're saying that we cannot reach 8.5 given everything. Am I right?
So based on all the data in the BGR assessment, which they are the best that I've found in terms of accuracy and in terms of rigor and how they integrate all these disparate data sources, that you would burn all of that and you still wouldn't reach the level of CO2, fossil fuel CO2 emissions to reach an RCP 8.5 scenario.
So we cannot exceed temperature rise of 3.2?
Well, so that gets into the ocean and land use factors because ultimately RCP 8.5, the integrated assessment models produce these emission scenarios, but only very few scenarios for the ESMs and GCMs are emission versus concentration, right? And so the 8.5 scenario was one of the few scenarios that was run with different ESMs that was emissions and concentrations in order to look at the differences. And that's because all of these parameters that would determine the land response or plants and CO2 uptake and fertilization, all those factors, they really play into if we have lower fossil fuel CO2 emissions, say in this range, could we still reach here with the worst case scenario? And then also other greenhouse gases too, right? Like methane and Arctic methane and those elements.
No, I agree. I think the conversation is that we still need to run RCP8.5, but the coal is not the reason. Maybe other reasons. We still haven't got the carbon tax right with Southern Oceans and the whole global oceans, carbon budget and then the feedback and things like that.
Yeah.
And then even for the impact assessment modeling work that most of us does, in this scenario, uncertainty actually, if you look at this century, it's paid a relatively lower role compared to the other part of uncertainty. It increased a bit in the end of century scenario uncertainty. But it also varies between the ocean. But then if you put in other socioeconomic scenario into it, the emission scenario uncertainty actually is much lower compared to, say, fishing uncertainty, things like that. So fine-tuning of RCP 6.0 and RCP 8.5, given all this scenario, and then we also have the deep uncertainty of the other things that we didn't consider.
Yeah.
It really doesn't doesn't. I think we are not. The community is not at the stage where we can actually say something that there will be a difference between RCP7.0 and RCP8.5. So I think the whole, and that's what I think one of the reasons why the impact assessment are based on these more bookend and scenarios and the one weekend, because that kind of level of things that we can say of the different future errors that we'll have in terms of the impact on different aspects.
Right. I wouldn't say that you can rule out RCP8.5 because there's just too many factors globally that could end up contributing towards it. Now, do I think that we can rule out the kind of emission scenarios that lead to RCP8.5? I think it's close to doing something like that, and I would wonder how that would affect the impact assessment process because, if you're using the RCP8.5 as the input and then looking at the impact versus the Earth system response that then is feeding back to create the RCP8.5 scenario, that's kind of where, that's at the limits of my understanding on how Earth system models would work. But that's the kind of area where I'd be more interested in learning about how that would happen. But in terms of the integrated assessment models and also the economics that they produce for policy interventions, these kind of mega pole scenarios are not useful anymore, especially when it comes to the policy front, because when you remove this high carbon, virtually limitless energy resource, it actually makes climate policy a lot more effective in the way that they're modeling it. Because all of these different energy technologies that had to compete with it, say solar or wind or efficiency that would potentially raise costs in various ways, well, if they're always running up against this limitless cheap supply, then they look like not as good of an option. And so in the integrated assessment model inside, when you take that cheap coal out and you actually make coal cost what it's costing now, it has a lot of different impacts.
And it's interesting that I think a lot of the literature lately, they don't look at the upper end, they're all focusing on the lower end, because that's kind of the Paris Agreement and people are trying
Right, like the RCP 1.9.
Yeah, fine-tune that component. So
Yeah.
that may be another reason that the latest version of the integrated system models have less focus on that kind of high-end scenario getting analyzed more. Because of the, they need to put in a lot of effort for doing that, especially reports and also into the assessment model communities trying to run that kind of scenario.
Justin, I'm wondering if you've looked at any of the other potential assumptions in some of these models. Like, what about? Have you looked at how models assumed energy efficiency would look over time versus?
Yeah. So if you're interested in this, actually, Charlie Wilson's coming through the IRES seminar series, and he was a former IRES student. And he just published a study as, I think he was the lead author, he was one of the first few authors in Nature Energy on what I would consider one of the first integrated assessment modeling studies that really did a good job at getting at what you're talking about, Gerald. And that's because so many of these scenarios were assuming that, post-World War II development with that kind of unabated, happy motoring culture, and that would just extend to all 9 billion plus people around the planet. And while there's some truth to that in terms of how development's gone, there's also just, you reach certain limits by trying to extend it out further. And so what Charlie Wilson did in this Nature Energy study was saying, what if we take some of the reasonable trends that are happening now with energy efficiency or with something called device convergence, where I can do more and more things on my mobile device, and what if I give up things around my house like a power-consuming television or Xbox or something like that that's eating 400 watts of power as you're being on, and I just replace it with this that has a little tiny battery and has barely any power draw. And then what if the model of development around the world and the global south is more around just skipping over these energy intensive modes of consumption and going straight to the new stuff, right? So I think, as in all of the 1.5 scenarios, it would be truly ambitious to actually have that kind of development pathway, but at least he's starting to put those trends, and he and his co-authors are putting those trends into integrated assessment models and looking at the kind of long-term climate impacts.
Can I ask a really quick follow-up? It's more kind of a devil's advocate kind of question. But so if we're, how likely is it that we're actually hitting kind of peak oil and stuff by like mid-century? And like if that's the case, would that increase the probability that we actually start going for coal because it becomes more competitive?
Yeah, so that's a good question, and I think that peak oil is something that will happen eventually because it's a geological feature where eventually you're hitting this point, and we keep finding more oil, and we're being more innovative in terms of new technologies. But you're going to reach a point, whether it's middle of this century or middle of next century, where you're just really at the maximum where oil is not competitive and it keeps being substituted out.
Yeah.
So I think 15, even 10 years ago, you could argue that maybe coal liquids could be the way that we might go, right? And I think the really big concern there was looking at what was happening in China in terms of building lots of coal liquids facilities and announcing government support for them. And then the government really pulled back because it requires so much water to do coal liquids. And you have this problem where a lot of the best coal producing regions are in arid areas. So you have to transport lots of water in to get to them. But what's happened with electric vehicles, I think, is starting to shift what that hypothetical might look like. Where if we reach a point that we have sustained high oil prices, either peak oil or geopolitical uncertainty, now it looks like the path of development of technology that's going to be the way of least resistance is just increased adoption of battery or hybrid electric vehicles. Yeah. Other questions?
No questions? Can I answer another one?
Yeah, let her right ahead.
You don't answer that.
Colette, it's two at the same time. You can do it. It's just that we all need the question. That was what the joke was about.
I know.
Okay. So, no, the thing is, if you look generally, I mean, when I see this thing, it reassures me, but I'm still skeptical, right? Because what this tells me, if I understand you well, is we are never going to shoot over 5% 5-degree increase. That is the kind of message that comes to me. But then you follow. But then if you look at all the projections, almost everywhere, whether it's overfishing or whatever, we always overshoot. You see the struggle I have. So how confident? Can I just sleep on this?
Right. I mean, that has to come back to the equilibrium climate sensitivity question, right? Because there's all these multiple layers of uncertainty, and let's say an RCP8.5 type CO2 concentration, like 900 or 1,000 parts per million CO2 happens. Then you have to look at what will be the temperature increase based on that level, and so then you have to go into the whole climate sensitivity literature. So. You definitely, in the same way you can't rule out RCP 8.5 level of CO2 concentrations, you can't rule out the 5-degree kind of increases. I would say it's less likely because of the coal issue, right? But
not
it's
completely,
still possible.
Yeah. Okay.
All right, any other questions? Okay, well, thanks. You've been a great audience. Thanks for the questions.